That's where the 9x flop reduction at 1 million tokens comes from. At shorter contexts, the ratio is smaller because the quadratic cost hasn't grown as large. At longer contexts, the ratio improves further. The selection ratio tells the story. At 1 million tokens, 2,048 out of 1 million survive. That is 0.2% of the context. The model is ignoring 99.8% of positions at each head, and betting that the 0.2% it keeps contains the information that matters. Jipu's claim is that this bet is lossless. The model with DSA performs equivalently to the model with dense attention on downstream tasks. The claim rests on a well-known property of softmax attention. The distribution mass concentrates heavily. In dense attention, even though every position gets a score, the vast majority of scores collapse to near zero after softmax. A handful of positions capture most of the weight. The long tail contributes almost nothing to the final weighted sum. DSA skips the tail instead of computing it, and then ignoring the result. The coding agent from earlier illustrates why this works. When the model at position 500, 000 queries for the cause of a key error. The positions that carry high attention weight are the function definition at 200, 000, the call site at 480, 000, and a few related import statements. Those positions appear in the top 2,048. The 997, 952 positions that contain unrelated code, documentation, and earlier conversation turns produce near zero scores and get filtered by the indexer. The model loses nothing by skipping them, but the selection is not free, and it creates two costs that the raw flop count doesn't capture. The first cost is cache fragmentation. A GPU stores the KV, cache the precomputed key and value vectors, for every token in the context in high bandwidth memory. When the model needs to compute attention, it fetches the relevant key value pairs from that cache. Modern memory hardware is optimized for sequential access. When the GPU reads key vectors for positions 1 through 2,048 in order, the memory controller can predict the access pattern. It prefetches the next block before the processor asks for it. The data flows through the cache hierarchy in orderly bursts. Dense attention exploits this perfectly. It reads every position in sequence. The access pattern is completely predictable. The memory hardware runs at peak efficiency. DSA breaks that pattern. The selected 2,048 positions are scattered across the full million token context. Position 47, then position 12, 903, then position 508, 221, then position 3, 400. The memory controller cannot predict the next address. It cannot prefetch. Every access is a random jump to a new region of memory.